Curve sketching. In previous chapters, we've seen how to sketch polynomial curves given in fully factorized form, certain exponential and logarithmic curves, and certain trigonometric curves. To sketch a general curve y equals f of x, we need to gather information about the curve. We can use the techniques outlined in this chapter. Very often, the information gathering steps are outlined in a question, but if not, the following are the features we should investigate. The intercepts. We can often find the x-intercept, where the curve intersects the x-axis, by putting y equal to 0. And likewise, we can find the y-intercept, which is where the curve intersects the y-axis, by putting x equals 0. Plotting these points then helps to locate the curve. The asymptotes. When any asymptotes exist, we should find them. In this case, drawing the asymptotes gives us a frame for the curve. The first derivative. Finding dy dx allows us to determine where the curve is increasing and decreasing and any stationary points. We can also use the first derivative test to determine the nature of each stationary point. So is it a maximum, a minimum, or a saddle point? The second derivative. Finding d squared y dx squared allows us to identify the nature of turning points, determine where the curve is concave upwards and concave downwards, and find any points of inflection. We may not be required to find all or indeed any of these features. Some types of curve require us to pay particular attention to one or more of the above features. Okay, so some types of curve require us to pay particular attention to one or more of the above features, so the features outlined on the previous slide. Type 1 polynomial curves. Finding the y-intercept is generally useful when dealing with polynomial curves. These curves have no asymptotes, but they may have stationary points and/or points of inflection. It is important to remember that we have encountered some polynomial curves before, and useful facts from our previous discussions can prove very helpful. The equation of a curve is y equals 3x to the power 4 minus 8x to the power 3 plus 6x squared minus 5. Part 1. Show that this curve has two stationary points, one of which is not a turning point, and find the coordinates of these points. So whenever we see mention of stationary points or turning points, we want to think differentiate. So here's our curve y equals 3x to the power 4 minus 8x cubed plus 6x squared minus 5. So dy dx, the first derivative, is 12x cubed minus 24x squared plus 12x. So we're going to factorize out the 12x, so we have 12x times x squared minus 2x plus 1, and then we're going to factorize what's inside the bracket, and we get x minus 1 times x minus 1, which gives us x minus 1 squared. So dy dx, the first derivative, is 12x times x minus 1 squared. So we put dy dx equal to 0. So we have 12x times x minus 1 squared equals 0. So x is equal to 0. Because if we let 12x equal to 0, then dividing both sides by 12 to get the x on its own, we get 0 divided by 12, which is just 0. So we have x is equal to 0. And then letting x minus 1 equal to 0, we bring the minus 1 over the equal sign, so we have x is equal to 1. So thus the curve has two stationary points, one at 0 minus 5 and the other at 1 minus 4. So in order to get these two y values, minus 5 and minus 4, we substitute each of our x values into the original function. So we have 3 times 0 to the power 4 minus 8 times 0 cubed plus 6 times 0 squared minus 5 equals minus 5. So when x is 0, y is minus 5. And likewise, we're subbing in the 1, we have 3 times 1 to the power 4 minus 8 times 1 cubed plus 6 times 1 squared minus 5. That equals minus 4. So when x is 1, y is minus 4. So here we have our two stationary points. So we've shown that the curve has two stationary points. Now we need to show that one of them is not a turning point. So because we are asked to show that one of the stationary points is not a turning point, we should use the first derivative test instead of the second derivative test. Then we take sample values on each side and between x equals 0 and x equals 1. So our sample values will be -1, 0.5 and 2, because these are either side of 0 and 1. And this can be laid out in the form of a table. So here's our table. The first row is our x values. These are our two actual x values that we worked out in the previous slide. And these are the x values either side of 0 and 1. Our next row is dy dx, our first derivative test. So we already know that when x is 0, dy dx is 0, and when x is 1, dy dx is 0. Now we need to work out what happens for x equals -1, 0.5 and 2. So at x equals -1, dy dx is going to be 12 times -1 times -2 squared, which is going to give us an answer less than 0. So we'll have a negative, we'll have a minus here for dy dx when x is equal to -1. Then for x equals 0.5, we have dy dx equals 12 times 0.5 times -0.5 squared, which gives us a positive answer. So that's why we have a plus in here. So when x is 0.5, dy dx is positive. And then when x is equal to 2, dy dx is equal to 12 times 2 times 1 squared, which is greater than 0, which is positive. So that's why we have a plus in here. So when x is 2, dy dx is positive. So then our third row is the shape. So when the derivative is 0, we just have a flat line. We have a horizontal line, horizontal tangent. And likewise over here, we'll have a horizontal line. When dy dx is negative, we have a decreasing function. When it's positive, we have an increasing function. And when it's positive, we have another increasing function. So this is the shape that our curve goes in. So from the table, 0 minus 5 is a local minimum. So we can see we would have a minimum point here. This is a U shape, so this would be a minimum point. And 1 minus 4 is a saddle point, because we see we are increasing, then we have a slope of 0, and then we're increasing again. So this is a saddle point. So therefore, only 0 minus 5 is a turning point. We can see that our curve is turning at this point, whereas here we have a saddle point. Part 2. This curve has 2 points of inflection. Find the coordinates of these points and describe the shape of the curve around each. So around each of the points. So when we think points of inflection, when we hear points of inflection, we want to think second derivative. So the first derivative, before we simplified it, was 12x cubed minus 24x squared plus 12x. So the second derivative, d squared y dx squared, is 36x squared minus 48x plus 12. So we're going to put the second derivative equal to 0. So we have 36x squared minus 48x plus 12 equals 0. We simplify by dividing across by 12. So we get 3x squared minus 4x plus 1 equals 0. Then we factorize. We get 3x minus 1 times x minus 1. And then we solve for x. So if 3x minus 1 is equal to 0, x is equal to a third. And if x minus 1 is equal to 0, x is equal to 1. So we have our two x values, a third and 1. So we are asked to find the 2 points of inflection and the coordinates of those points. So now we have the x values, we next have to find the y values. So we substitute the x values into the original function. So for x is equal to a third, we swap each of these x values for a third. So we get 3 times a third to the power 4 minus 8 times a third plus 6 times a third squared minus 5 is equal to minus 124 over 27. So when x is equal to a third, y is equal to minus 124 over 27, which is approximately equal to minus 4.59. And then we substitute x equals 1 into, again, our original function. So we swap each of these x values for 1. So 3 times 1 to the power 4 minus 8 times 1 cubed plus 6 times 1 squared minus 5 is equal to minus 4. So when x is equal to 1, y is equal to minus 4. Thus, the points of inflection are a third minus 124 over 27 and 1 minus 4. So the curve is concave upwards to the left of a third and to the right of 1. It is concave downwards in between. So we know from previous videos that if the second derivative is greater than 0, so positive at C, whatever the point C is, then the curve is concave upwards at C. So if we take the x value of a third, well, a point to the left of that, an x value to the left of that would be 0. So if we were to substitute 0 into our second derivative, we'd have 36 times 0 squared minus 48 times 0 plus 12. So we'd have 12, which is positive. So we know that to the left of a third, x equals a third, the curve is concave upwards. So concave upwards to the left of a third. And then if we take our x value of 1 and we take a value to the right of that, so let's say 2. So if we were to substitute 2 in place of each of these x's, we would have 36 times 2 squared minus 48 times 2 plus 12, which is equal to 60, which is positive. So again, when the second derivative is positive, the curve is concave upwards. So we would have concave upwards to the right of 1. And we know that when the second derivative is less than 0, so when the second derivative is negative, the curve is concave downwards at that point. So if we take an x value somewhere in between a third and 1, let's say a half, and we were to substitute a half in place of each of these x values, we'd have 36 times a half squared minus 48 times a half plus 12, which would end up giving us minus 3, which is negative. So in between, we have concave downwards. Part 3, sketch a rough graph of this curve. So here's our x-axis, here's our y-axis. And our curve is 3x to the power of 4 minus 8x cubed plus 6x squared minus 5. So since it's a polynomial, we know we don't have any asymptotes, so we can't draw in the frame of our curve. If we let x equal 0, we can find our y-intercept. So if each of these x values was to be 0, we would be left with y equals minus 5. So therefore 0 minus 5 is going to be our y-intercept, the point at which it crosses the y-axis. And this is also our local minimum. So this is the lowest point in our graph. We also know we have a saddle point at 1 minus 4. And we know we have points of inflection at 1 minus 4 and a third minus 124. And we know that in between a third and 1, we have concave downwards. And to the left of a third, we have concave upwards. And to the right of 1, we have concave upwards as well. So this is just a rough sketch of our graph. Now we'll have a look at what the graph really looks like. So here we have the actual curve of y equals 3x to the power of 4 minus 8x cubed plus 6x squared minus 5. Type 2, other curves. For other curves, we go through any information gathering steps that may be outlined. In the absence of these, we follow the guidelines at the beginning of this section. For curves of the form y equals u of x divided by v of x, it is important to consider asymptotes. Example 2. F of x maps to 1 over e to the power of x minus 1 is a function defined for all x values elements of the real number set where x is not equal to 0. Part 1. Find the vertical asymptote and the two horizontal asymptotes of the curve y equals f of x. So for the curve y equals 1 over e to the power of x minus 1, to find a vertical asymptote, we let the denominator equal to 0. So we have e to the power of x minus 1 equals 0. So e to the power of x equals positive 1. So x equals log base e 1. And log base e1 gives us 0, so therefore x is equal to 0. So we have a vertical asymptote at x is equal to 0. Now let's find our horizontal asymptotes. So horizontal asymptote, right. So y is equal to the limit of 1 over e to the power of x minus 1 as x approaches infinity equals the limit of 1 over e to the power of x divided by 1 minus 1 over e to the power of x as x approaches infinity, which is equal to 0 over 1 minus 0, which is equal to 0. So what we did was we divided each term by e to the power of x, because that's the highest power of x, which is the same thing as multiplying each term by 1 over e to the power of x. So 1 multiplied by 1 over e to the power of x is 1 over e to the power of x. E to the power of x multiplied by 1 over e to the power of x is 1. And minus 1 multiplied by 1 over e to the power of x is minus 1 over e to the power of x. And as x approaches infinity, so the closer and closer and closer that this x value gets to infinity, the bigger the denominator gets in this fraction. And 1 over infinity will basically give us 0. And likewise for minus 1 over e to the power of x tends to minus 0. So therefore the horizontal asymptote on the right is y equals 0. Now the horizontal asymptote on the left. So we have y equals the limit of 1 over e to the power of x minus 1 as x approaches minus infinity. So we swap this minus infinity for positive infinity, and we swap each x value for minus x. So we have the limit of 1 over e to the power of minus x minus 1 as x approaches positive infinity equals the limit of 1 over e to the power of x minus 1 as x approaches positive infinity equals 1 over 0 minus 1. So therefore y is equal to minus 1. So there was no need to divide each term by e to the power of x here because e to the power of minus x is actually 1 over e to the power of x. So we already have this in the form that we wanted. So as x approaches infinity, the denominator in this fraction here gets bigger and bigger and bigger, and 1 over infinity tends to 0, so that's how we get 0 here. So we have 1 over 0 minus 1, which is 1 over minus 1, which is minus 1. So the horizontal asymptote on the left is y equals minus 1. Part 2. Show that the curve y equals f of x is decreasing for all x values elements of the real number set where x is not equal to 0. So our function is y equals 1 over e to the power of x minus 1, which can be rewritten as e to the power of x minus 1 to the power of minus 1. So when we hear increasing or decreasing, we want to differentiate. So we're going to differentiate this function, and we're going to use the chain rule, which is the outside multiplied by the inside. So we differentiate the outside, we multiply it by the derivative of the inside. So differentiating the outside, we differentiate the power, keeping the base. So differentiating the power, the minus 1 comes down in front, so we've minus in front, or minus 1. And then minus 1 is minus 2. So we've differentiated the power, and we've kept the base on the inside. And we multiply that by the derivative of the base. So we differentiate the inside. And the derivative of e to the power of x is e to the power of x. Next we multiply. So minus times e to the power of x is minus e to the power of x. And e to the power of x minus 1 to the power of minus 2 gives us 1 over e to the power of x minus 1 to the power of positive 2. So we end up with minus e to the power of x over e to the power of x minus 1 squared. And as minus e to the power of x is less than 0, and e to the power of x minus 1 squared is greater than 0, for all x values elements of the real number set, when x is not equal to 0, dy dx is less than 0, and the curve is decreasing for all x values elements of the real number set where x is not equal to 0. So we have a minus divided by a plus gives a minus. So therefore the derivative, no matter what the x value, will be minus. So dy dx, the derivative is less than 0, so the curve is decreasing. If it had been greater than 0, the curve would be increasing. So minus divided by a plus is a minus, so it's decreasing. Part 3, draw a rough sketch of the curve y equals f of x. To sketch the graph, we start by drawing the asymptotes. So we have an asymptote at x equals 0, which is basically the y-axis. and we have an asymptote at y equals minus 1. So from the left, the curve approaches the line y equals minus 1. So we can see that as we're coming in from the left, our curve is very, very, very close to minus 1, but it doesn't touch it. It then decreases as it approaches the vertical asymptote x equals 0, or the y-axis. So it then decreases and gets closer and closer and closer to the y-axis, but it doesn't touch it. As the curve is decreasing everywhere, it comes from plus infinity on the y-axis. So it comes from plus infinity on the y-axis down to the horizontal asymptote on the right, i.e. the x-axis. So down to the horizontal asymptote, the x-axis. So that was just a sketch, but here we have the actual curve drawn out. So again, we can see our horizontal asymptote at y equals minus 1. And we can see the other horizontal asymptote at y equals 0. And we can see the vertical asymptote at x equals 0.